So, this is my answer key. Have I introduced you guys to my favorite student? My favorite student, her name is... Why don't I turn the freeze off? There's my favorite student. Evan, can you read that to me? Ann Surkey. She gets everything right. It's amazing. I love it. I don't get it. Huh? Explain it to the other people around there. Okay. Oh, some of you just got the joke now? Okay. Ancient times, what did some Greek philosophers believe? What did you put here? Sure, Ev.
The matter could be divided endlessly into smaller and smaller pieces.
Okay, I don't want to write that much, so I'm going to abbreviate because I tend to do that. So they thought that you could, did you say divide? Do you mind if I go like that? That might be a good abbreviation for the word divide, yes? Matter into, like if you guys abbreviate when you text messages, if you can do that in your notes, now not on a test, don't expect me to translate your abbreviations, but in your homework and your studying, absolutely. When you go to university, by the time you get there, if you haven't figured out some kind of abbreviated note system, if you try to write down everything profs say, your arm's going to fall off. In fact, you'll find when you go to university, there's this standard abbreviation system that kind of has evolved over about 100 years that you'll pick up. For example, that's the word which, and that's the word why. You just notice other people writing the notes that way. You learn all sorts of little abbreviations along the way. You learn little Greek abbreviations. Anything you can do to not write out everything, because if you're trying to write as fast as a prof talks, it just doesn't happen. So you could divide matter into, and I'm going to say this, smallest chunk. In other words, you could keep dividing, but eventually you get a piece that was so tiny, it would keep slipping out from underneath your knife, or however you want to think about it. They named that smallest piece of matter atomos, or atomos. I'm not sure how to pronounce it in Greek, from which we get the word da-da-da-da, atom. However, Aristotle was a very, very influential philosopher. He was the pupil of Plato. Socrates. Anyways, he wrote a book that for about 2,000 years defined how all of the world, at least all of Europe, thought science should be. And it was all wrong. It's all wrong. If any of you take me for Physics 11 and Physics 12, you'll hear me go on a big rant about how Aristotle set science back by about 2,000 years. But he did. What did he say? He said that everything was made up of what? If you've wondered in video games where that whole earth, wind, fire thing comes from, it actually is from the Greeks. So he said that matter was made up of, I'm not going to write that phrase, earth. I think he said air, we say wind. Or no, he did say wind, never mind. Fire and water. He thought everything was made up of four things. He said that explains why human beings are warm. They got some fire in them. Oh, it also explains why when you bleed, there's some water in you, that's some blood. Bad explanation. He really didn't think it through properly. But at the time, they didn't do anything like a scientific method with hypothesis and experiment and prove or disprove or anything like that. They just tried to reason it out and they ended up with the wrong conclusions. Then we had the alchemists. These were scientists trying to turn what into what? All right, John Dalton, the 4 points of his theory. And I think I had 4 points on your notes, write a little chart there, I think. I don't know if we'll write them out word for word. Again, we may try to abbreviate. What was the first thing that he said in his theory? Because he was getting much closer, so we kind of consider him the father of our understanding of chemistry. No? Oh, okay. Danielle. Okay. All matter. I'll drop the word is, made, I'll drop the word up, of, small, I'm going to go part with a period, that'll be my abbreviation for particles, called, and this was the big thing, he named them atoms after that old Greek theory. Okay. By the way, I haven't really explained how he came to that conclusion, but what he noticed was when he was looking at compounds, when he was breaking them down, he kept noticing, for example, that when he split water up into hydrogen and oxygen, he always had twice as much hydrogen as oxygen. Always. 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 And when he split other carbon dioxide is CO2, he noticed he always had twice as much oxygen as carbon. Always. Always. And so he started to think maybe every substance is a combination of smaller chunks, and maybe the reason the ratios are the same is those smaller chunks are as small as it gets. Maybe you can't go further than that. Now, we now know he was technically wrong because he didn't know about protons and neutrons and electrons. And I've told you that protons and neutrons and electrons are technically wrong. You can go smaller and get quarks, but we're going to pretend that you can't. Okay. B. What's the next thing he said? Yeah. I think DEST, you know what, I'll do destroy, that'll be pretty good. I'll figure out that's destroyed or destruction, destroyed. Or what was the third one? Oh, or divided into smaller pieces. What else? Third thing. And now he's getting really important. Kevin, right? Yeah.
All atoms of the same element are identical
He-
in size and mass.
He said you can't tell, it's impossible to tell the difference between one oxygen atom and another oxygen atom. They're identical in size and mass. And we now know even in subatomic composition, every oxygen, you're going to learn this later on this week or next week, every oxygen atom has the same number of protons, same number of neutrons, and the same number of electrons. As long as it's its basic atom. We can muck around with that after, but when we're starting out. Okay? So you said all atoms of same element are identical. I like that. And then the fourth one, this one's a little more obscure, but now he's going backwards to where he came from. He started out looking at compounds. He said, I think they're made up of smaller chunks. Then he said, well, that means, yeah.
Compounds are made when atoms of different elements link together in definite proportions.
Compounds are made of, I'll say, proportions of atoms. In other words, carbon dioxide is always one carbon, two oxygens. If it's not, it ain't carbon dioxide. What if it's one carbon, three oxygens? That's something different, and it might have very different chemical properties, even to the point of maybe carbon dioxide might be a gas and maybe carbon trioxide might be a solid. I don't know. Why is it impossible to turn lead into gold? You don't know this yet, but maybe the textbook told you. The reason is lead has more, what's P plus an abbreviation for? Protons. What you're going to find out when we start looking at the periodic table is that an element is defined and is what it is because of the number of protons it has. If it has 8 protons, it's oxygen. If it has 1 proton, it's hydrogen. 2 protons, it's helium. In fact, it goes in order. If you look at the back of the room there, that red letter H, 1 proton is hydrogen. Go all the way across, there's an orange HE. 2 protons is helium. Go down to the next row, Li. Lithium has 3 protons. If it doesn't have exactly 3 protons, yeah, it's all, now you just figured out how to tell time in my room. I saw her eyes light up. Oh, that's why it goes hydrogen, helium, lithium, 3 protons, beryllium, 4 protons. The number of protons is what determines what an element is. The number of electrons determines how it will combine with other stuff. The number of neutrons determines whether it's radioactive or not. You don't need to know that. That's the next unit, but preview of coming attractions, hashtag nerd trivia. Okay. By the way, we have abbreviations for all of the elements. If you look back there, you can write every element with 2 letters. So if you really wanted to be lazy, you could go look up, look up, look up, look at the front, look at the front, look at the front, look at the front, look at the front. Hey, look at the front. You could go, that's the abbreviation for lead. and that's the abbreviation for gold. Those two don't make much sense. Why is lead PB? Because not all elements were discovered by English-speaking people, but most of the element abbreviations make sense, and you'll memorize the more common ones. You don't have to. You'll have a chart with all of them, but you're going to get lazy, Franz, and you'll memorize the ones you write the most often because it's less writing, which is, again, the only reason you should memorize stuff, in my opinion. Dalton's model of an atom resembled, I'll say, a billiard ball or a lacrosse ball. I'd say tennis ball, but tennis balls are hollow, and his atom was solid and chunky, one thing, so not empty. Then we had J.J. Thomson. He came along and he discovered charged particles called, I don't want to write the word electrons. It would be handy if there's a lovely, oh, there is a lovely little abbreviation. He proposed that atoms were made of charged particles. He said, you know what? Because he noticed that every atom had a charge of 0, but he could get a negative charge out of it, he said there must be a positive charge left behind. That way when you go positive plus negative, your charge is still 0. Okay, that was his reasoning. His model of an atom resembled chocolate chip muffin, chocolate chip cookie, raisin bread, plum pudding model if you want. It's always been affectionately called the plum pudding model in his honor. So I'm going to say sorry. On your test, I am going to ask you as a written question to describe Rutherford's experiment, okay? And in particular, to tell me what it means. So, what was his famous experiment? Fired alpha particles. You don't have to remember that they're called alpha particles. You can just say particles, but as a science nerd, I'm going to say alpha particles. In fact, it turns out there's an abbreviation for alpha. I would just write that. That's an alpha, which is where our letter A comes from, which is the Greek letter A. Anyways, in case you're wondering, hashtag nerd trivia. So he fired alpha particles at thin sheet of gold foil. What happened? Two things. Most of them, okay, I'm even going to say almost all went straight through. I know that's not how you spell through. I told you in my notes I'm going to abbreviate, right? What does that mean? What could he conclude from that? That was his first conclusion, since almost all of them went straight through. Yeah?
There's just nothing there.
Atoms are mostly empty space. Like, I think 999,999 out of a million empty space. But then we had some were you know what? Were deflected is the fancy science word. Bounced. Rebounded. That's a better word. That's also not much writing. Rebounded. Some rebounded at angles, but a few rebounded like straight back, which is what really got his attention. Conclusion.
Well, how do you know they rebounded straight back? Because there was no like color or the thing.
Well, by straight back, what I really mean is they bounced back at about like an 80-degree angle, because this was a very long, painstaking experiment in a dark room. I showed you the video of the modern equivalent because we can detect them now. He was doing it with a piece of like almost like the glow-in-the-dark moons and stars for wallpaper. It was almost that kind of material. So he had it all dark, and it would very briefly glow or phosphoresce when one of the particles hit it. So he was literally staring. Holy smokes, something over here glowed. Why would it have bounced back at almost a 90-degree angle, about an 80-degree angle? So when I say bounce straight back, but also he said, you know what, that must mean some were probably coming straight back, and I'm just not detecting them because I had to cut out that piece of phosphorescence.
Oh, yeah.
Great question. So what was the conclusion if some rebounded? Right. Yep. And because I can't really call it heavy because the nucleus is ridiculously light, but for its size, it's ridiculously heavy. Oh, That was density. That's why I brought up that lead ball, which had the same size as that other one. Something really small and dense in the middle, colon, what did he call it?
Nucleus.
I'll even put that in capital letters because it's pretty important. And yes, that's where the word nuclear comes from. Nuclear physics is mucking around with the nucleus, which we couldn't do for a while because it was tucked inside the atom. In 1945, they learned how to split the atom. There's the nuclear age. Okay? So he discovered the nucleus, which is a tiny, dense. My mom says I'm dense. No, that's a different kind of dense. Positively charged center, which for some reason in Canada we spell R-E, even though most of you probably spell it E-R, but whatever, I'll take either. But I'm a proud Canadian. I'll spell it the Canadian way. Then he later, by the way, why is the nucleus positively charged? Well, one of the particles in there is the proton, the proton. He later found, though, that there was actually another particle in there that had no charge. So he later discovered the nucleus contains two types of particles, protons and neutrons. You can write the words out. We have lovely abbreviations, and I tend to abbreviate. Which ones are positively charged? Protons. Which ones have no charge? You have to be a little bit careful because every year there's a kid that goes, oh, neutrons are negative. Sorry, that also begins with it. Neutrons are neutral, have no charge. So his model, not quite right yet. He said, okay, I have protons and neutrons in the middle, and then he kind of figured that the electrons were kind of scattered. He had them outside, but he didn't know quite how. He might have had some here, some. He knew they weren't in the nucleus, is all. He knew that. Then Niels Bohr came along, and this is where it gets weird, but it explains an awful lot. In fact, Niels Bohr won a Nobel Prize, and then Einstein about a year later. Einstein never won a Nobel Prize for his theory of relativity. He won a Nobel Prize for explaining why things glow in the dark by taking Niels Bohr's idea of the atom and showing that also explained this idea of levels, explained why things glow in the dark, or why things glow when you heat them red hot, why things glow when you add energy. So Niels Bohr, he showed that electrons surround the nucleus in what?
Shells.
Our word is going to be shells. So draw an, by the way, this diagram of the atom as we know it today, it's actually, I should change that because it's not as we know it today. This is the Bohr model, and we're going to use this, Ibrahim, because it explains a lot. But first of all, understand, Alex, atoms are three-dimensional. I should be drawing shells this way as well as this way. Well, we can't draw that on a piece of paper. That's yucky. And it turns out as shells get bigger, as you get more and more electrons, they start to tangle and overlap. We're not gonna go there, Brooke. We're gonna start with our fairly basic one, and this will explain like 90% of what's going on. So I always have to tell you, Brian, this is wrong, but this is what I'm going to ask you to reproduce on the test because it's pretty good. It's a model, and it's a pretty good model. What did he say? He said, here's the nucleus with protons and neutrons. Then he said, there's a close or an inner shell. He also found out that that inner shell can only hold 2 electrons. If you try adding a third one, it won't fit into that shell. It's going to go into the next shell. He found that the next shell holds 8 electrons. And not only that, he found that electrons, first of all, would go singly, 2, 3, 4, and then when you added a 5th one, they tended to pair up. I'll stop there, but you could add 7 and 8. Then if you wanted to add a 9th, it wouldn't work. Boom, that would go in the next shell. And it was weird because he found it was impossible for the electrons Leave the ball alone, Cole. It's called an attention span. It's impossible for the electrons to exist in this white space right here. So if an electron moves from here to here because you give it more energy, it's here, it vanishes, it no longer exists in the universe, and now it's here, but it did not cross the path in between. They do, I'll use the word teleport. It's actually more complicated than that, but that already, Maddie, makes it, this sounds like Harry Potter and witchcraft. On the quantum level, some of that stuff on the subatomic level happens, and it's even weirder than that. Most of the stuff that happens with protons, in particular with electrons, I can't explain using words for stuff that you're familiar with in the big world, because it behaves totally bizarrely. I like this chart, I like this chart, I like this chart, I like this chart. Why would I say that?
Because it's going to be on the test.
Did you hear me say that? You're kind of student tends to know those things? Okay. Proton, neutron, electron. If the electron weighed 1 kilogram, it doesn't. It weighs like one. Well, an electron weighs 0.000000000 31 zeros, and then a 9 and a 1 and a 1. So it kilograms. So, but if it weighed 1 kilogram, what would the proton weigh? 1,500. And what was it?
One more.
What is it? 1,837. And a neutron would be 1,800 and... By the way, it's the other way. That's what I thought. I thought that was wrong. I think the neutron is heavier. You know why? Because all a neutron is if you, inside like a star, like the sun or something like that, if you press a proton and an electron together and you fuse them together, now you have a charge of 0, and that's where a neutron comes from. And that's why a neutron weighs exactly 1 more than a proton. There you go. Electric charge, +1, 0, -1. Nuke, shells. How can the charge on an atom be 0 if it contains charged particles? Well, 9 protons plus 9 electrons equals, what's 9 positives plus 9 negatives?
0.
Or if you really want to go further on the periodic table, like what's 87 positives plus 87 negatives? Still 0. Most atoms in their normal state, in their neutral state, they have a charge of 0. Now, if you want them to do stuff, all we do is we muck around with the charge. What are we mucking around with? The electrons, because they're on the outside and much easier to move around. Any questions there? So if you want to hand this in today, you can. If you want to hang on to it until Tuesday, because you want it to study from, you can. I'm not going to enter any marks this weekend or anything like that. Okay? So, Chapter 2, Section 2.1. What makes up the universe? Well, the word we're looking for here is elements and the periodic table. Here's where I think it gets more interesting. Now, I am going to say also, it is going to get tougher, but I'm going to try and go system. If I do my job right, whenever we come to something that's tough, if I've done my job right, at the end of it, you'll say, oh yeah, that makes sense. I wouldn't have thought of that, but based on what I knew already, okay, that fits into what I already knew. That's my goal. We'll start out with a Richard Feynman quote, not in your notes. Richard Feynman, one of my physics nerd heroes, he won a Nobel Prize. He said this: if, in some cataclysm, all scientific knowledge were to be destroyed, and only one sentence could be passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or atomic fact, or whatever you want to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling each other when being squeezed into one another. In that one sentence, you will see an enormous amount of information about the world if just a little imagination and thinking are applied. I think you already know that thing in bold font. Certainly that would explain how solids, liquids, and gases work and why that when you add heat that occurs. But it explains even more, if we're clever. So I have for you a pink periodic table, and I'm going to be giving you a little worksheet. This is just to get you familiar with the periodic table. Cats are composed of iron, lithium, and neon, because that spells feline. You're going to learn that they all have abbreviations. Let me pause the video for a second and show you what I mean. So I have this little sheet here that I called Exploring the Periodic Table. Kids always freak out about the front page. I'm not as concerned so much about the front page, but keep your pink periodic table handy, and the front part of it, not the back page, so the part that has the big, well, that thing on the back wall, like that thing. In other words, basically flip your periodic table over. That's the page you want to be looking at. That's what I'm getting at, okay? The back page we'll get to later, but for now, the big charty front, no, flip it over. That's the front of the periodic, that thing, okay? Yeah, okay. So it says this: each box on the periodic table represents a specific element. We'll be learning how to use the periodic table, but first step, I kind of like kids to just get used to looking around and seeing where stuff is. As you look at the name of the elements, you'll notice that some of the names are familiar, hydrogen and oxygen. What number is, like I said, you want your pink periodic table out, Trevor. There you go. What number is hydrogen? Element number what? 1. What number is oxygen? Element number what? I'm going to ask you the same question. I'm going to phrase it differently, but I want the same answer. What's the atomic number of hydrogen? 1. What's the atomic number of oxygen? 8. See it? See oxygen? Okay, it goes in order of atomic number, not alphabetically. What's the atomic number of potassium, which is on the left side somewhere? What's the symbol for potassium? Because I want to know. Okay, because I want to know. Okay, because I want to. You want to hear a joke about potassium? Okay. You want to hear a joke about sodium? Nah. So you're going to find dumb periodic table, because what's the symbol for sodium, which is right below potassium? Na. Or is it above potassium? So the joke we always have, you want to hear a joke about potassium? Okay. You want to hear a joke about sodium? Nah. There's your first science nerd joke. They're going to get worse. Now, what's the atomic number of sodium? 11. What's the atomic number of potassium? What's the atomic number of iron? The symbol for iron is Fe, 26. I'm going to ask you the same question, but I'm going to phrase it differently, and you're already going to learn how to read the periodic table. How many protons does sodium have?
23.
Sodium. How many protons does sodium have? I want the same answer you said, 11. How many protons does potassium have in its nucleus? How many protons does iron have in its nucleus? In other words, that number actually already tells you a lot. I got even better. How many electrons does sodium have? How many electrons does potassium have? How many electrons does iron have? 26. That number there tells you the number of protons, number of electrons. It does not tell you the number of neutrons, though. I'll get to that later. But there's a lot of information there. And you'll notice every time you add one proton, the atomic number goes up, and you're a whole new element. An element is defined by how many protons it has. So if something has 13 protons, what element must it be? Go find it. If something has 13 protons, what element does it have to be? Aluminum. And it probably has 13 electrons, but we can muck around with the electrons in real life, so it might not. If something has 27 protons, what element must it be? Okay. What else do you notice? As protons go up, there's another number. You know what? I should have the periodic table open right here, shouldn't I? There's another number at the bottom, and this one is often a decimal number. That's what we call the atomic mass. Turns out, as you move to the right, as you add more protons and neutrons and electrons, Brooke, go figure, the atoms get heavier. How many protons does lead have?
82.
Ooh, he found. Now, what's the abbreviation for lead? LE? PB. Why? So once again, we're going to go hashtag nerd trivia. It comes from the word plumbing. I kid you not. Because the Romans happened to name lead with, it's the Latin word for lead, which is PB, because the Romans made their pipes out of lead for all their aqueducts and all their plumbing. What they didn't realize was they were also giving themselves lead poisoning, which explains a little bit of why the Romans were a little bit crazy. Anyways, PB, so there's a history behind most of these abbreviations. Most of them make sense. Now that you've got a little familiar, take a look back at the handout that I gave you, Exploring the Periodic Table. These are supposed to be terrible puns for numbers 1 to 8. They're terrible. We brought everything but the kitchen. Well, zinc isn't an element. Can you find me one that might look like the kitchen zinc? And there's your hint. What is zinc? Element number what? And by the way, this is how we'll find stuff. You'll tell me what the, until you get good, you'll memorize where a lot of these are because you get sick of looking at them. But otherwise, what's the atomic number? What element number is zinc?
30.
30 or 12? The top, I want the top number, not the decimal.
30.
Is zinc element number 30? I'm looking back. Yeah? Okay. What's atomic element number? Someone was saying 12. That's that's either magnesium or manganese. I can't read from back here, but it's Mg. Okay, zinc. So the joke here would be, we brought everything but the kitchen. And I'm not going to write zinc. I'm going to use the abbreviation because I tend to abbreviate. And I'm going to say from now on, you never need to write out the name of an element unless it specifically is required. If you're in your homework and you just want to use the abbreviation, great. Dial 911 to call a copper. They're going to be that bad. I'm not marking these right or wrong. These are brain teasers that I want to talk about after your test next week on Thursday. Okay? So try numbers 1 to 8. Then, translate this poem. Hey, what was PB? You led me to believe he's dead. You can get the words and you can come up with a little poem here. It's bad. Okay? Then you can complete this story by filling in the blanks. What I have in brackets here is the atomic symbol. So you're not going to write AU. You're going to say, what the heck is AU? AU! No, it actually, it's a particular element. Okay? See if you can fill in the blanks here. And then on the back, still more blanks. And then the very last thing I have, here is a crossword puzzle where your clues are the symbols and you'll write the names of the elements in the crossword puzzle. This is all just to get you familiar with where stuff is kind of laid out. Any questions there? No. Okay. Now the only difference is, just like I mentioned earlier that center in Canada is spelled R-E and in the US it's spelled E-R, sulfur in the US is spelled with an F, in Britain is spelled with a PH. And that's why I put a little PH right there. And if you're ever doing, you may notice, I think that's the only one. You may notice another one that doesn't quite work. If there's an F, replace it with a PH because I stole this from a British website and it'll be fun. When is this due?
Tuesday.
Why Tuesday? You have a test Tuesday. When is this due?
Next Thursday.
Okay, so I'm going to say here. Now, you can get it done, probably most of you in class. And Cole, if you want to get it done for Tuesday, great. Again, you guys are in grade 9. Know what your schedule next week is like, what evenings you're busy or wanting to watch TV, what evenings you're not. Spread it out. But I'm going to be giving you more stuff on Thursday.